Hi, my name is Michael Duda, and in this lecture we're going to look at the fundamental capabilities of the WRF Pre-Processing System. And before we start, it's useful to have some perspective, so we can take a look at the WRF modeling system flowchart. And sitting here at the center of the flowchart is the ARW model itself. This is the component of the modeling system that takes initial conditions and advances them forward in time. And the initial conditions for the model generally fall into two different categories. The first category is what we describe as idealized initial conditions. These are initial conditions that are typically generated from analytic formulas and that don't in general correspond to the state of the atmosphere at any specific point in time over any specific part of the Earth's surface. And those idealized initial conditions are in contrast to what we call real data initial conditions. Real data initial conditions are initial conditions that are intended to represent the state of the atmosphere at some specific point in time over some specific part of the real Earth's surface. And there are four different components of the modeling system that might be involved in the production of real data initial conditions. So if you trace all of these paths backwards, you'll find that all of the paths to produce real data initial conditions ultimately originate at this component of the modeling system called the WPS. So we can say then that the WPS is the component of the modeling system that is used to configure real data simulations. So in this lecture, we're going to focus on the basic usage of the WPS to firstly define a single simulation domain. And if you're familiar with WRF, you might be aware that it supports region refinement through a technique called nesting. And there's a separate lecture called Nesting in WRF that describes this process. Once we've talked about how to set up a simulation domain, we're going to talk about how you can use the WPS to pre-process time-varying atmospheric and land surface data sets. These are data sets that provide typically analyses of fields like atmospheric temperature, atmospheric humidity, atmospheric winds, soil moisture, soil temperature, and sea surface temperature. And then lastly, we're going to talk about how to use the WPS to horizontally interpolate these data sets to be used as initial and boundary conditions in your WRF model simulation. There's a second lecture on the WPS that covers the steps to actually running all of the components that we're going to talk about in this lecture. And there's a third lecture on the WPS that talks about advanced features. So, as we'll see in this lecture, the WPS isn't a single program, but it's three main components. So there's a component called Geogrid that takes as input these static geographical data sets, which we'll take a look at in just a few slides. There's a component called Ungrib that takes as input these gridded data sets that can come from different sources, and we'll take a look at that in just a few slides. And there's a component called Metgrid, which combines the output of the Ungrib program and the Geogrid program. And the output of the WPS is ultimately fed to this other component of the modeling system called the real preprocessor. So the first of the components that we're going to talk about is the program called Geogrid. And the geo part of the name Geogrid comes from the fact that this is the program that does the geographical processing on your WRF model grid, hence the name Geogrid. So we can easily understand the purpose of the Geogrid program by supposing that we wish to perform some real data simulation for the cartoon domain shown here on this slide. In looking at this cartoon, we can start to ask questions like, where is this simulation domain located? So there's a mountain range, and does that mountain range represent some small series of hills, or does it represent the Rocky Mountains, or does it represent the Himalayas? And we can also wonder, what area does this domain cover? So is the span of the domain just several hundred meters, or does it span a distance of thousands of kilometers? And we can also start to wonder how well the simulation resolves the atmosphere and the land surface in the horizontal directions. So we can see in this cartoon that there's a lake, and we transition to deciduous forest and now into needle-leaf forest. And so how many grid cells do we have that resolve that transition on the land surface and in the atmosphere above? And we can also ask questions like, what sources of data do we use to represent the topography in this domain and the different vegetation categories in our domain? And so from the perspective of the WRF model, It's the Geogrid program that we use to answer all of these questions. So when we set up a real data simulation using the Geogrid program, there are essentially 4 things that we need to do. The first thing we need to do is to describe a map projection that will be used to flatten the curved Earth surface onto a projection plane. Once we've done that, we can determine the geographic locations where our domains will be located, and we can also describe the dimension of our domains in terms of the west-east distance and the south-north distance that our simulation domain spans. We can also specify the number of grid points in the west, east, and south-north directions, and this dictates the horizontal resolution of our model domain. Once we've done these 4 things, the Geogrid program has all the information it needs to ultimately provide values for what we call static or time-invariant fields at every one of the model grid points. And this happens by first computing the latitude and longitude at every one of those grid points. And because we have the details of the map projection, these latitudes and longitudes can be calculated through analytic formulas. The Geogrid program also calculates map scale factors and Coriolis parameters at every grid point. And given latitudes and longitudes, we can then horizontally interpolate from global data sets values of static terrestrial fields like topography height, land use categories, soil type, vegetation fraction, and climatological monthly surface albedo, and various other fields. Now, we said that the first thing we need to do when we set up a simulation domain using the Geogrid program is to choose a map projection, and it might not be obvious why we need to do this. Essentially, the real Earth surface is something like an ellipsoid, but as we've seen in the WRF introduction talk, our WRF domains are defined by rectangles on a plane. So we need some way of flattening the curved Earth surface onto a plane. There are many different map projections, but there are only 4 that are supported by the Geogrid program for ARW simulations. So the first of these is the Lambert conformal conic projection. The second is the Mercator projection. The third is the polar stereographic projection. And the fourth is the latitude-longitude projection. And if you intend to run a global simulation using the ARW, you have to choose a latitude-longitude projection. So in the next few slides, we're going to look at each of these map projections in turn. So the first of these projections is the Lambert conformal conic projection. And this is formed by taking a cone and setting it over the northern hemisphere of the Earth or over the southern hemisphere of the Earth. And once we've done that, we project rays out from the center of the Earth through the Earth's surface and onto this cone. And that defines a mapping between points on the Earth's surface and points on the cone. There are 2 special latitudes in the Lambert conformal conic projection, and these are called the true latitudes. These are the latitudes at which this projection cone is either tangent to the Earth's surface or intersects the Earth's surface. And they're called the true latitudes because at those latitudes there is no distortion of scale. You can easily see that there is some distortion of scale by taking 2 rays and noticing that from the points where they intersect the Earth's surface to the points where they intersect this projection cone, they either diverge or have yet to diverge further. After we've projected the Earth's surface onto this cone, we can cut the cone along a longitude line and flatten it out into a plane. So typically, these true latitudes are chosen to be around mid-latitudes, again, either in the northern or southern hemisphere of the Earth. And so this means that this projection is typically used for mid-latitude domains. Now, looking over here at this part of the figure on the right, you can see that because there's a wedge missing over the North Pole, obviously we couldn't cut out a rectangular simulation domain that contained the North Pole because there would be a wedge missing. And the opposite pole is spread infinitely far away. So as a consequence, you can't use the Lambert conformal conic projection if you would like to run a simulation over either pole of the Earth. This projection also doesn't permit you to run periodic simulations that have periodic west-east boundary conditions where flow going out the eastern side of your domain comes back in the western side. And that's easily seen because there's no way to cut out a rectangle from this projection plane such that the western edge is coincident with the eastern edge. The second projection is the Mercator projection, and this is formed by taking a cylinder and wrapping it around the Earth. And it can either be tangent to the Earth's surface at the equator, or it can intersect the Earth's surface at plus or minus some latitude. And similar to the Lambert conformal conic projection, there is a true latitude, and again, that is the latitude where this projection surface either intersects the Earth's surface or is tangent to the Earth's surface. This true latitude is typically taken to be at lower latitudes, and so as a result, the Mercator projection is a popular projection for use in low latitude simulations. Because this is a cylindrical projection, it's also possible to cut out a rectangle on the projection plane such that the eastern boundary of the domain is coincident with the western boundary, so that flow going out the eastern side comes back in the western side. So it is possible to define what is called a channel domain using the Mercator projection. The third projection is the polar stereographic projection. This projection is formed by taking a plane and setting it over the northern hemisphere of the Earth or the southern hemisphere of the Earth. And this time, rather than projecting rays out from the center of the Earth, rays are projected from the opposite pole through the Earth's surface onto this projection plane. And because the projection plane is already a plane, there's no need to make any cuts, and we can simply look at the projection plane on our screen. So as the name suggests, this projection is good if you want your domain to contain either the North Pole or the South Pole by using a southern hemispheric polar stereographic projection. And in general, it's good for simulation domains that are centered over higher latitudes. For example, if you wanted to run a simulation over Greenland, the polar stereographic projection might be a good projection to choose. The final map projection that's supported by the ARW is the cylindrical equidistant projection, also known as the regular latitude-longitude projection. And in this projection, there aren't really rays that pass through the Earth's surface onto a projection plane. We simply lay out the Earth's surface on a plane with equally spaced latitudes and equally spaced longitudes. So as I said earlier, if you intend to run a global simulation with the ARW, you have to choose this projection. And you can rewind and convince yourself that this is the only projection among the four that we've talked about that allows you to cover the entire Earth's surface without any missing wedges or gaps. So in describing a map projection to be used for our ARW simulation domain, there are a set of parameters that we need to define in the Geogrid program. And the first of these is called map_proj, and this is a character string that indicates which projection we intend to use. So one option is to set this parameter to Lambert to indicate a Lambert conformal projection, Mercator to indicate a Mercator projection, polar for polar stereographic, or lat-lon to indicate a regular latitude-longitude projection. Depending on which map projection we're setting up, we may need to specify either one or two true latitudes. And if we're setting up a latitude-longitude projection, we can optionally specify pole latitude and pole longitude to rotate the pole of the projection away from the North Pole of the Earth. And the rotation of latitude-longitude grids is described in more detail in Chapter 3 of the ARW User's Guide. Lastly, there's a parameter called standard longitude, which is not formally part of the map projection, but it describes the longitude line that's parallel to the y-axis in our model grid. So if you rewind a couple of slides back to the polar stereographic projection description, you can imagine that by selecting different longitude lines, we could change the orientation of Antarctica so that either the Antarctic Peninsula were pointing north in our domain or the Ross Ice Shelf were pointing north. And that's the usage of the standard longitude parameter. In the second WPS lecture about running the WPS, we'll see how we set all of these parameters in a file called the nameless.wps file. So we've spent several minutes talking about map projections, and you may wonder why it's so important to choose among these different map projections when setting up a model simulation domain. The idea is that different map projections and their associated parameters distort distances differently over different parts of the globe. And the important point is that in WRF, the geographic grid distance at any point in your model domain is given by the nominal grid distance that you choose when you set up your domain, divided by something called the map scale factor. And this map scale factor is a two-dimensional field that describes the scale distortion inherent in different map projections. So the important idea is that the maximum stable time step that you can use in the WRF model is determined by the geographic grid distance in your model domain and not the nominal grid distance. So if you have, for example, map scale factors that are much larger than 1, you're going to have geographical grid distances that are significantly smaller than your nominal grid distances, and that is going to generally necessitate the use of a smaller time step for a stable integration in the model. After you run the Geogrid program, you'll be able to look at the two-dimensional map scale factor field in the Geogrid output file. And you can do this, for example, using a program called NCView. And we'll take a look at that in just a couple of slides. So in this slide, we're looking at an illustration of the sorts of differences that we might see in a model simulation domain when we choose a different map projection and different parameters of that map projection. So in both cases, on the left and on the right, what we're looking at is the terrain height field from a model simulation domain that we've set up with the Geogrid program. And we're rendering that terrain height field from our model grid onto an orthographic projection of the Earth's surface on both the left and the right. Now the model simulation domain on the left was set up in the Geogrid program using a Mercator projection with a true latitude of 42 degrees north. And with this choice of projection and true latitude, we get map scale factors that range from about 0.82 to 1.22. And if we had chosen a nominal grid distance for our simulation domain of 12 kilometers, this would mean that we actually have geographic grid distances in our domain that range from about 9.9 kilometers all the way up to 14.6 kilometers. So quite different from our nominal distance of 12 kilometers. Now on the right, we've set up our model domain using the Geogrid program with a Lambert conformal projection and true latitudes of 30 degrees and 47.5 degrees north. And with this choice of projection and true latitudes, we get map scale factors that range from 0.988 to 1.023, so only about a 2% deviation from the ideal value. And this means that our geographic grid distances for a 12-kilometer nominal grid distance go from about 11.7 kilometers to 12.1 kilometers. So both of these domains cover roughly the same geographic area, shown here on the left and shown here on the right, but by simply choosing a different map projection that's better suited for mid-latitudes, we can get much less scale distortion in our model domain. So we stated earlier that the map scale factor field is a two-dimensional spatially varying field. And after running the Geogrid program, you can easily check the range of map scale factors in your model domain and that are related to your choice of map projection and map projection parameters by opening up the NetCDF output from Geogrid using, for example, the NCView program. And you want to look at one of the fields called mapfac_something. There are map scale factors in the x direction, map scale factors in the y direction, and map scale factors at various staggerings of model grid points. But the easiest one to look at is mapfac_m. This is the map scale factor at the mass staggered points. And you can see that it's a spatially varying field. And in this particular example, we can see that our map scale factors range from about 0.81819 to about 1.22. And this actually is the Mercator projection that we set up for our domain in the previous slide. So after we've done the work of flattening out the Earth's surface onto a projection plane, we can then specify to the Geogrid program the geographic location and size of our model domain. And so we can do this with a set of parameters that are illustrated in this cartoon here. So reference latitude and reference longitude specify to the Geogrid program the latitude and the longitude at the geometric center of our simulation domain, which is represented by this white rectangle here. Once we've specified the geographic location that's at the center of our domain, we can then specify the extent and resolution of the domain in the nominal west-east direction using a pair of parameters. Delta x is the spacing between grid points in the west-east or x direction, and EWE is the number of velocity staggered points in the west-east direction. And similarly, in the nominal south-north direction, we can specify delta y, the spacing between the points in the y direction, and ESN, the number of velocity staggered points in the south-north direction. So we can summarize the parameters that were illustrated on the previous slide as follows. Reference latitude and reference longitude are the latitude and longitude at some point in our model simulation domain, and by default, they refer to the geometric center of our course domain, although it is possible to have these latitude and longitudes refer to some other grid point in the model domain. And this is described more in detail in Chapter 3 of the User's Guide. dx and dy give the nominal grid distance, which corresponds to the true geographic grid distance in the parts of the domain where the map scale factors are identical to 1. For Lambert conformal, Mercator, and polar stereographic projections, dx and dy are specified in meters, and for the latitude-longitude projection, dx and dy are given in fractional degrees of latitude and longitude. And then lastly, EWE is the number of velocity staggered points in the nominal west-east direction, and ESN is the number of velocity staggered points in the south-north direction. So once we've described the map projection on which we'd like to define our model domain, and we've described the geographic location and size and resolution of our model domains, we can then run the Geogrid program. And as we said earlier, the Geogrid program goes and it computes latitudes and longitudes for every one of our horizontal grid points. And once it's done that, it can then use global data sets to interpolate fields like topography height, land use categories, soil type, annual mean soil temperature, and quite a few others. So after the Geogrid program finishes running, it writes its output into netcdf files. And you get one netcdf file per simulation domain. Those output files are named geo_em.d0n.nc, where n is the domain number. So if you were setting up a single simulation domain, you would get an output file called geoem.d01.nc. The NC part of the file name refers to the fact that this is a netcdf file, and the geo part of the name, of course, refers to the fact that this is a Geogrid output file. If it wasn't already mentioned in the introduction talk, EM is the old name for the ARW dynamical core. It stands for Eulerian mass, which is the vertical coordinate that's used in the ARW. So here we see some examples of output fields that you would expect in these Geogrid output files. So in the upper left, we have a land mask field. This is a 0-1 field that indicates in our model grid which grid points are land and which grid points are water. In the upper right, we're looking at the topography height field. So this tells the model how high the terrain elevation is at every grid point in the model domain. In the lower left, we're looking at an example of a categorical field that describes the soil texture category. And in the lower right, we're looking at one of the climatological fields that's produced by the Geogrid program, and this happens to be the vegetation fraction for the month of January. So having looked at the Geogrid component of the WPS, we're now going to look at the component called Ungrib. And the name of the Ungrib program comes from the fact that it works with a file format called grib, which we'll talk about in just a couple of slides. And effectively, it undoes this grib formatting of datasets. It converts grib datasets into a format that's much easier to process by the Metgrid program. So you may have experience with grib files in the past, and if not, you may be wondering what exactly a grib file is. Well, grib is a WMO standard file format for storing regularly distributed fields. And more often than not, regularly distributed simply means that these are gridded fields. So grib stands for General Regularly Distributed Information in Binary. And all of the fields that are stored within a grib file are compressed with various compression methods, and more often than not, it's lossy compression in order to make the files as small as possible. So in the simplest of these compression methods, you can think of taking all of the values in a field and truncating those values to a fixed number of digits. Now, grib is a record-based format, so it means, for example, that you can take two grib files and concatenate them together to get one big grib file that contains the union of all of the fields in the two original files. And it also means that it's possible in principle to process individual records or fields from a grib file. And importantly for our discussion to come is the fact that the fields in a grib file are only identified by code numbers. So if you're given a grib file without any additional information, you would have a hard time figuring out which field is which. You would know that there's a field number 33 and there's a field number 61, but you wouldn't know whether field number 33 represents temperature or humidity or pressure or something else. So what we need is external tables against which we can reference these code numbers. And we'll see how that factors into the Ungrib program in just a few slides. So the Ungrib program is capable of processing two different versions of the Grib format. There's Grib Edition 1 and Grib Edition 2. And if you intend to process newer Grib Edition 2 files, when you compile the WPS, you'll need to link against additional compression libraries. So the entire purpose of the Ungrib program is to extract meteorological and land surface fields from Grib files and to put them into an easier to process file format that we call the intermediate format. The Ungrib program is capable of doing some very basic derivations. For example, it can compute relative humidity from temperature, pressure, and specific humidity. But essentially, it's just a program that pulls out fields from Grib files and writes them to what we call intermediate files. So when the Ungrib program is processing a Grib file, how does it know which fields it needs to extract from that Grib file and write to an intermediate file? This is specified using variable tables, which we refer to as vtables in WPS terminology. So vtables are files that list all of the Grib codes that correspond to fields that need to be extracted from a given Grib file. So different sources of Grib data typically use different codes to refer to the same field. So as a consequence, we need different vtables for different sources of data. But when we provide the WPS, we provide vtables for many common sources of Grib data. For example, CFSR, ERA Interim, GFS, NAR, and quite a few others. So in this slide, we're looking at an example of a Grib Edition 1 vtable. So in the left 4 columns here, this is the information that the Grib file uses to identify fields. So this Grib file, we can see, has parameter number 33, field number 33, at level type 100 and all levels, and there is no level 2 for level type 100. And the 3 columns on the right correspond to the human readable names that we would like to identify these fields with when they're written by the Ungrib program into intermediate files. So we know now that after Ungrib finishes running, in our intermediate file, we'll have a field called U, which is, well, it happens to be the zonal component of the horizontal wind given in meters per second. For Grib Edition 2, there are some additional parameters that are needed to identify fields, and these are appended to the right as 4 additional columns. So these are things like discipline, category, parameter, and a level type. So if you intend to process a source of Grib data for which we don't already provide a vtable, what do you do? In this case, you'll essentially need to create your own vtable, and the easiest way to go about this is to first get a listing of all of the Grib codes for the fields in this file, and this information should be given to you by whoever produced the Grib file. The second thing that you probably want to do is to take any existing vtable and use it as a template, and to simply go through and change all of the codes to match the codes that are used in your Grib dataset. There's more information about the contents of these vtables in Chapter 3 of the User's Guide. So if you look around page 3-35, you'll see more information on vtables and which fields are required by the rest of the WPS. So after the Ungrib program finishes running, it will have extracted all of the fields that are needed to initialize a real data simulation, i.e. those fields that are listed in the vtable corresponding to your Grib dataset. And the Ungrib program will have written all of those fields to an intermediate file. So if you wanted to use a source of meteorological data that wasn't provided in Grib format, that is possible, but you'll need to circumvent the Ungrib program. Essentially, you'll need to take your non-Grib data and to write it to this intermediate file format. Chapter 3 of the ARW User's Guide provides more information on this intermediate file format. And along with the WPS, we also distribute 2 Fortran modules called ReadMet module and WriteMet module that can serve as examples of code that can be used to read and write these intermediate files. So essentially, if you have meteorological data that are not in Grib format, you'll need to process that data and write it yourself into the intermediate file format that the rest of the WPS can use. So after the Ungrib program finishes running, we have a set of intermediate files. And in general, we have 1 file per time period of data that was processed by the Ungrib program. So the names of these files by default are simply file, and then colon, and then a year, month, day, and hour. And that year, month, day, and hour is the valid time of the data in that intermediate file. And all times are UTC. So for example, if we had GRIB data that provided us meteorological data for 12 hours from 2007 July 24th at 0 UTC through 2007 July 24th at 12 UTC every 6 hours after running the Ungrib program, we might expect to see 3 intermediate files corresponding to data at 0, 6, and 12 UTC. The last of the main WPS programs is the Metgrid program, and it combines the output from the Ungrib program with the output from the Geogrid program. You can easily remember the function of the Metgrid program by recognizing that the Met in the name Metgrid refers to the fact that this program processes meteorological data on the WRF model grid. The primary purpose of the Metgrid program is to horizontally interpolate the meteorological data that were extracted by the Ungrib program onto the simulation domain that we defined using the Geogrid program. Some meteorological fields are masked in that they have missing values, and the Metgrid program needs to take this into account when it does its horizontal interpolation. It's also worth pointing out that although the Metgrid program can process data on isobaric and native vertical coordinate levels, the horizontal interpolation takes place along coordinate surfaces. A secondary purpose of the Metgrid program is to rotate the horizontal wind field so that the components are relative to the x and y axes in the model grid. When performing its horizontal interpolation, the Metgrid program directly interpolates meteorological fields to their proper staggering in the ARW grid. And this means that the U component of the horizontal wind field is interpolated by the Metgrid program directly to the U staggered points in the ARW grid, and the V component of the horizontal wind field is interpolated directly to the V staggered points in a grid cell, and all other scalar valued fields are interpolated directly to the centers of the grid cells. We said earlier that the Metgrid program needs to take into account masking when it performs its horizontal interpolation. And when we talk about masked fields, we're referring to fields that might only have valid data at a subset of their grid points. A common example of a masked field is the sea surface temperature field, which is often only provided with valid values over water. The Metgrid program needs to know which points to use and which points to ignore when it performs its horizontal interpolation of masked fields. And there are 2 different ways that the Metgrid program can know which grid cells contain valid data and which contain invalid data. The first possibility is that a GRIB dataset comes with a separate field that identifies land points and water points. This is typically called a land sea field, and it's usually a 0-1 value field with 0 over water points and 1 over land points. The second possibility is that every field uses a special missing value to identify invalid points in that field. So on this slide, we're looking at an example of masked interpolation. So let's suppose that we wanted to interpolate to this X, and that represents perhaps the center of an ARW grid cell. And these circles represent values in the source grid from which the Metgrid program needs to interpolate. So blue circles represent valid data in the source grid, and red circles represent invalid data or masked out data. So the Metgrid program, as we'll see in the advanced WPS lecture, provides several different methods for horizontally interpolating fields, and the Metgrid program needs to properly choose which of those methods to apply for masked fields. So for example, in this case, we couldn't do a bilinear interpolation to the target location because one of the values surrounding that target location is missing. But we could, for example, do an average of any 4 surrounding points that were not missing. So here we're looking at an example of the sort of masked interpolation that might take place in the Metgrid program. So on the left panel here, we're looking at a plot of our example model domain. This is a high-resolution ARW domain centered over the Pearl River Delta, and what we're looking at is just the land use index field. So the estuary is clearly visible as blue points here. In the center panel, what we're looking at is the sea surface temperature data set that's provided on a 1/12 or 0.083 degree grid. And you can see that the SST field doesn't exactly line up with water points in our ARW model domain. So if we overlay land points on top of this SST field, it's obvious that there are some water points in our model domain that aren't covered by the SST dataset. And conversely, there are some land points that are covered by the SST dataset. So the Metgrid program handles these mismatches in land sea mask between our ARW domain and the SST dataset when it performs its horizontal interpolation. So it's even possible to use masked interpolation for fields that are valid everywhere, and we can see an example of that on this slide. So on the left panel, we're looking at the skin temperature field that has been interpolated from a half-degree GFS dataset onto a high-resolution model domain over the eastern United States. The skin temperature field is valid everywhere, so we can do something simple like apply a 16-point interpolation stencil everywhere, and the result is certainly a valid skin temperature field. However, if we'd like to get a better definition of the high-resolution coastlines in our model domain, we can tell the Metgrid program to interpolate the skin temperature field from GFS to land points in our high-resolution ARW domain only using land points in the GFS data. And similarly, we can say to interpolate to water points in our ARW domain only using water points in the GFS dataset. And by doing that, you can see that we get a much better resolution of the high-resolution coastline in our model domain. You'll also notice that we now have distinct skin temperature values for all of these lakes, these inland water bodies in our high-resolution domain. And you may notice that some of these lakes are substantially warmer than the surrounding land points in the skin temperature field. This is a problem that we refer to as the hot lakes problem, and we'll talk about how we can address this problem in the advanced WPS lecture. So besides interpolating meteorological fields, we said earlier that it's also the job of the Metgrid program to rotate the horizontal components of the wind field so that they're relative to the ARW grid. So typically, datasets are provided with two components of the horizontal wind, a westerly component and a southerly component. But because our ARW domains are often laid out on a map projection, the westerly component of wind isn't always the same as the X component of the wind, and the southerly component of the wind isn't always the same as the Y component of the wind. So the Metgrid program needs to rotate the wind field so that its components are with respect to the X and Y directions in the model grid. So here we can see an example of rewriting the same wind vector with respect to a different basis. So we can imagine that this blue vector here represents the true wind vector, and the U component represents the westerly component, and the V component represents the southerly component of this wind vector. After the Metgrid program finishes running, the Metgrid program will have rewritten the same wind vector so that it's with respect to the X and Y directions in our model grid, because that's what the ARW solver expects from the wind field. Although the Metgrid program typically is used to process time-varying meteorological fields, it is possible to treat time-invariant fields specially with the Metgrid program. One application of this is for short simulations, where we might want to hold certain fields fixed throughout the duration of the simulation. For example, if we were running a real-time simulation starting today, we might not have a future SST field to use in our simulation. In this case, if our simulation is short enough, it's a reasonable approximation to take today's SST analysis and to use that as a fixed SST field for the next couple of days in our simulation. In the Metgrid program, the way that one specifies constant fields is with a special namelist option called constants name. In that case, the entire name of an intermediate file is given, and every field contained in that intermediate file will be held fixed throughout the ARW simulation. After the Metgrid program finishes running, we get one netcdf output file per domain per time period that was processed by the Metgrid program. So all of these netcdf output files contain the static fields that were in the Geogrid output, plus the horizontally interpolated meteorological fields that were processed by the Metgrid program. These file names have the form shown here, metem.d0n, year, month, day, hour, and sometimes minutes and seconds. So n is the domain number, and as with the Ungrib program, the year, month, day, and hour are given in UTC time. After running the Metgrid program, It's often a good idea to use something like NC-View to open the NetCDF output files from the Metgrid program and see that some of the fields in them look reasonable. On the slide, we're looking at some fields that might be worth checking. An example of a land surface field that's masked is the soil moisture field. An example of an unmasked atmospheric field might be the relative humidity field at some chosen pressure level. We also have fields that are valid at the surface, like skin temperature. We have typically a mean sea level pressure field, and we have other meteorological fields throughout the depth of the atmosphere. So we can summarize the work of the WPS as follows. The Geogrid program is the program that we use to define our simulation domains and to interpolate time-invariant geographical data sets onto those domains. The Ungrib program is used to process meteorological fields from GRIB files and to write those data into a very easy to work with format. The Metgrid program horizontally interpolates meteorological fields onto our model domains, and the output of the Metgrid program then is passed off to the real preprocessor. That's discussed in a separate lecture. And it's the real program that handles the vertical interpolation from isobaric or native vertical levels onto the ADA levels that are used in the WRF solver.